This video will tell you everything you need to know about real numbers and square roots, how we get from the whole numbers to never-ending decimals. So when we first started the DMA courses, you worked only in the whole numbers, numbers like 0, 1, 2, 3, 18, 95, etc., etc. But we found out that those numbers weren't enough for all of the operations that we did. So we expanded our group of numbers to include the opposites of the whole numbers. Numbers like -1, -2, -3, -18, -95, and so on. Those two numbers were grouped together in a single group called the integers. Now, as we moved into our current course, we began to realize that the integers weren't enough to include all of the operations that we could do. So we expanded our set a little more to include fractions, or answers when we divide an integer by a non-zero integer. Numbers like 1/2, which is 1 divided by 2, or 14/5, which is 14 divided by 5. Since we can let either number be an integer, this would also include numbers like -3 divided by 10, or 75 hundredths, the decimal, which is an answer to 75 divided by 100, or 8 divided by 1. Now, since you can take any integer and divide it by 1 and get 8 over 1, or 12 over 1, or -7 over 1, that means all of the integers would be included in this group of fractions. So we call this group of numbers the rational numbers, and it is any number that can be written as p divided by q, where both p and q are integers and q is not equal to 0. Well, as we saw a little earlier in our course, even this doesn't actually include all the operations that we can do, so we have to expand this set one more time. This part of the set of numbers includes some numbers that you may be familiar with, like pi. It also includes other numbers that may not be as familiar to you, like a number that is used quite often in calculus, e. Now, it also includes other pretty recognizable numbers like the square root of 29, and also like the decimal number 1.1213, 1234, 12345, etc., etc., etc. This decimal number is irrational because the decimal portion of it does not end, nor does it repeat. If you remember, whenever you write a fraction as a decimal, it will always end, or it will be a repeating decimal. Since this decimal does neither, it's what we refer to as a irrational number, which simply means that it's not rational. In other words, it can't be written as an integer divided by an integer. Now, there are no numbers which overlap these two groups. A number has to be either rational or irrational. But if we take all of those numbers together, we get the group that mathematicians call the real numbers. Most of your work from here on out will be done only in the real numbers. Remember that the real numbers are made up of several smaller groups of numbers. The whole numbers, which were part of the integers, which were part of the rational numbers, grouped together with a separate set of numbers, the irrational numbers. So we can see from this diagram that, for example, the number 3 is a whole number, it's also an integer, and it's a rational number, and it would therefore also be a real number. But a number like the square root of 29 is only irrational and real. Now, speaking of irrational square roots, it was mentioned earlier that the square root of a non-perfect square, like the square root of 29, is irrational. That is, it cannot be written as an integer divided by an integer. This also means that the decimal portion of this number does not terminate and does not repeat. So, how do we write it? Well, the answer is we can't write it any other way than to write it as the square root of 29. All we can do is to write an estimate of it, round it off to some useful decimal place. For example, since the square root of 29 equals 5.385164, 8071, and so on, and so on, and so on, we might write that the square root of 29 is approximately 5.4. Or we might say that the square root of 29 is about 5.39. Or that it is approximately equal to 5.385. Or perhaps, if we wanted to be extra precise, we might say that it's approximately equal to 5.3852. Or we could just keep going as many decimal places as it needed in order to serve our purpose. One thing you should always be able to do with a non-perfect square, even without a calculator, is to be able to tell which two consecutive integers its square root is between. To do this, find the largest perfect square that's less than 29 and the smallest perfect square that is greater than 29. In this case, it would be 25 and 36. So, since 29 is between 25 and 26, and we know the square root of 25 is 5, while the square root of 36 is 6, that means that the square root of 29 would have to be somewhere between 5 and 6, the square roots of 25 and 36. We also know that it is closer to 5 than it is to 6, because 29 is closer to 25 than it is to 36. So as a rough estimate of the square root of 29, we know that it is probably somewhere between 5 and 5 5/10. On the next slide, pause the video and try one for your own. Find the two consecutive integers that the square root of 77 is between, and tell which one it is closer to. I'll give you just a minute to pause the video and to work on that. I hope you got it. Since 77 is between the perfect squares 64 and 81, and because the square root of 64 is 8 and the square root of 81 is 9, that means the square root of 77 is somewhere between 8 and 9. We can also say that since 77 is closer to 81 than it is to 64, that's because 81 minus 77 is only 4, while 77 minus 64 is 13. The square root of 77 has to be closer to 9 than it is to 8. When you need a more precise estimate, you can use a calculator. On the modulus estimate, you will not be asked to find a precise estimate, only to find what two integers a square root might be between and which of the two integers it is closer to. You are now ready for the MyMathLab assignment that is linked right in this item. Please have it done and turn it in before midnight.